and in our images. Okay. So now you have seen that there are some processes in the sensor. When we acquire an image, there are some processes that create noise. And we will see now how we can deal with things, where things come from and how we can deal with them. So signal, background, and noise. We have something called the signal to noise ratio and the signal to background ratio. And unfortunately, very often people clump them together. And this is very, very common. So most people are going to call everything signal to noise ratio. And then it's often abbreviated SNR. But the reality is that signal to noise and signal to background ratio are very different. They have different causes and they have different solutions. So you should not aggregate them. And same thing when you see something in your images that you don't like, just don't say, oh, it's background, and ignore it and pretend it's not there. You have to figure out, where does that come from? Why is it there? What can I do about it? Because it can be very important as well. So why do we care about background? Well, you see this little ball in the grass here. We can say, oh, this is our interesting signal. And that, oh, this is very boring. We don't want to see this in the image. What we would like to see is the whole ball. Well, what is the difference between background or noise? Is this background or is this noise? The background does not change from one image to the next. The background is real fluorescence. It's just, we call it background because we don't want it, but it is actually real fluorescence. So if you take 2 or 3 images, it's still going to be there because it still fluoresces. Whereas the noise is very different. The noise is random. So you take 2 images, the noise is going to come at different places because it's random. And the noise is not real fluorescence. The noise comes from the imaging process. So you can see that we have different problems and we have different solutions. So it's important not to aggregate them. So we often call background everything in the image that we wish were not there. For example, the offset of the detector, any antibody that sticks all over the place. Oh, this is autofluorescence, background. The mounting medium is fluorescent, it's background. Everything is background. And then afterwards, when we talk about the quality of the image, we say signal to noise ratio for everything. So let's put it clearly. These are different things. So knowing where background components come from will help you eliminate them. So it's important to tackle these sort of things. And then if you, the idea with this signal to noise ratio, signal to background ratio, which basically help us understand the contrast in the image. And I've already told you how important the contrast is, otherwise we cannot use the resolution. Well, if we want to improve our signal to background ratio, we can do 2 things. We can work on the background and we can work on the signal, and we will increase the ratio regardless. Most people think about the signal, they just want more signal, but they forget to lower the noise and the background. So we can work on both the noise and the background, or increase the signal, and we will get an improvement of the signal to noise ratio and the signal to background ratio.
Sorry, can I ask you a question here? So about the offset, if we increase it, it means that we are actually increasing the background, right?
Yes.
Because
if you put it very high, then you will get like everything becomes gray at the bottom.
Yeah, exactly. Because one thing that I was trying to do is to increase offset, because I wanted because I was basically underexposing my sample. I could see this blue dots.
Yeah.
So when I increased, I got rid of them, but then the background was like bluish. So what should I, because
yeah, so we will talk about it a little bit afterwards. So today and tomorrow we will talk about that. So I think you will get your answers. But basically, the quick answer is the offset of the detector when you work with a single point confocal sets the lowest level of sensitivity of the detector. You don't want this lowest level to be too high, because otherwise you will artificially prevent your detector from detecting weak signals that you want. But if it's too low, then we see everything outside that has some sort of a color. It's very easy to remove it afterwards anyway, because you can remove this.
Thank you.
You can remove this with the display, so it's not an issue at all. It's more of an issue if you set the value too high, because you will prevent the detector from detecting weak signals. If you set it too low, it doesn't matter, because you can, so it's the opposite. Sorry, if you put it too high and then you see that the background is a bit blue, doesn't matter, because that is easy to fix afterwards. But if you set the offset too low and you cannot detect the weak signals, then there's nothing you can do afterwards if the image has been acquired that way. But we will talk about this a little bit afterwards.
Okay, thanks.
So signal, background, and noise. Here we have a beautiful zebrafish that I used to study during my PhD. And you can see we say, oh, this is a very interesting signal. Oh, this is very bad. Why do we have all this green in the background? It's exactly like you said, Af. Oh, why is my background not black? I would like my background to be black. It doesn't really matter. This can be removed. So, and this is even more boring background. You can see that this boring background that we're not interested in is even much stronger than the interesting signal that we're interested in. So how do we deal with that? Yes, the background can be even stronger than the signal. So let's have a look a little bit at signal and background. So here we have an artificial image with little squares. And so we have set the background. So the image is always the same intensity on the outside of the little squares. And we are changing the intensity of the little squares. They become brighter from one image to the next. So the signal is the intensity, what we define as signal. It means the intensity in the pixels we're interested in. That is the signal. And then the background is the intensity outside the pixels we're interested in. Okay, the signal, the place we're interested in, is also called region of interest. So this is used very much in image analysis, region of interest, or ROI. So we will encounter region of interest in this course as well. So it means the signal of the pixels we are interested in. So we make a choice. I like that one, I don't like that one. Yeah, we make a choice here based on our scientific question, maybe based on what we know about the sample. Sometimes based on what we wish. Sorry. Okay. So here we have a background everywhere that is 100. Now, whereas the signal changes, and you can see that the signal increases a lot from one image to the next. Here we have 5,000. And so we calculate the signal to background ratio simply by dividing the signal by the background, and that's the ratio. So we go from here a signal to background, and it's not the real values at all. So it's just to illustrate. So the signal to background ratio of 1.5 with very low, where we can hardly distinguish the little squares, to an image highly contrasted, where we have a signal to background ratio of 50. So what is good? Which one do we need? The one you need is the one that allows you to extract a reliable answer for your scientific question. And so it's not easy, because it depends on the scientific question, it depends on the technique that you're using, and it depends on how you analyze the images, and the the acquisition of meaningful and reliable data is definitely different from acquiring beautiful images. Fortunately and unfortunately, microscopy is a very visual technique. So we look at it and we want beautiful images. And this is really not a good idea. So you can focus on acquiring meaningful, reliable data. This is for hardcore science, what you want to actually acquire and analyze. And then once in a while, you also acquire a very beautiful image, because you want to have some to put in your papers when you want to publish. And maybe you're going to be invited to have the cover of Nature. You need a beautiful image. So then your aim is to acquire a beautiful image. Go for it. But do not acquire beautiful images all the time. So you need to rely on data, what is reliable, and not your eyes, basically, and your brain. So now we have seen how we can increase the signal to basically improve the signal to background ratio. So how can we increase the signal? In fixed samples, we can definitely push the illumination power. So we're going to get a higher signal. We can use longer exposure time. We can slow down. So in camera-based system, we can slow down the scan speed, as we said, increase the pixel dwell time. So how long the scanner stays on each pixel. With point confocals, we can do some averaging. We can talk about this a little bit later. Binning, if you remember, binning the camera means that you put the signal that comes from 4 pixels together. That's bin 2, and to make one big pixel. So you're going to get one pixel that is much brighter, but clearly the resolution, the digital resolution will be lower. And if we have a point confocal, we can use larger pinholes. So all these things will increase the signal. But you have to be careful, of course, with bleaching. If you do a Z-stack, if you push the illumination power, if you do any of these things, it means you're going to be bleaching more, and especially during a Z-stack or a time-lapse, or if you need to re-image the samples later, you need to be careful with bleaching, and yes, so that has to be considered. And if you don't care about bleaching, don't be afraid. I see people all the time who are going to be imaging with 1% of the light and never change this. Ooh, no, I'm not going to go to 10. Well, there, bleach your sample. What you want to do is you have spent a lot of time preparing that sample, designing the whole thing, I don't know, doing lots of stuff. What you want out of it is not to keep the sample. What you want out of it is meaningful images. So getting meaningful images that will give you reliable data analysis, if that goes through bleaching the crap out of your sample, do it. By any means, just blast the thing with the illumination power and get very good, very solid data. And then you throw away your sample, and that's okay, instead of keeping it in the fridge to decay. So do not be afraid of increasing the illumination power. This is an excellent, and very reliable way to increase the signal in your images. If we have live samples, that is different, right? We have to be very gentle with the live sample. And as we have seen yesterday with the lecture, we need to be very careful that our imaging parameters preserve the biology that we are observing. If you're imaging, if you want to analyze mitochondria, you do not want the imaging process to influence your mitochondria in any way. So it's very important that the imaging does not influence the biology that you're observing. So you need to be very conservative with live samples. There you want to have the minimum light exposure that requires, that allows you to analyze the images and get meaningful data. So there you might go through a different number of rounds where you say, okay, I'm going to go even lower with my illumination. Can I still analyze the images? Is this still reproducible? No. Okay, well, I go up a little bit more. What happens to my cells, etc., etc. So with live samples, it's a little bit more hard work. With any type of samples anyway, you should never have any saturation and underexposure. So we're going to talk about it, I think, tomorrow. Yes, tomorrow we'll talk about saturation and underexposure. So in any case, never saturate and have any underexposure in the area of interest. And that regardless of which system you use. Always test the whole pipeline from sample preparation all the way to image analysis. You learn at each step, then you go back and you do more iterations of this. This is a very important process. Do not stop at one step and say, I'll do it that one done, and then I will move on. This is a recipe for failure. So do not spend a lot of time acquiring a lot of images without testing the analysis pipeline. So now if we look at the different situation where we're going to, instead of changing the signal, we're going to change the background. So you can see that we go from this situation where we have a signal of 500 to, and the background of 1. So we have this good signal to the background ratio, to another situation where we have a poor signal to background ratio because the background has increased. So clearly you can influence both the signal and the background. And so do not forget to influence the background. So the background can come from two different places. So I will tell you what it is now. It can come from the imaging conditions and it can come from the sample. So I remind you that background is real fluorescence. It is not the same thing as noise. So if the background comes from the sample, where can it come from? So we've heard this a little bit in the lifestyle imaging, or I don't remember which lecture. It can come from the culture medium. So we have different, so if we go in Fiji, I have here two different samples, or the same samples, but one of them has, I don't remember what it was, but anyway, one of them had some cell culture medium and the other one had PBS or something like this. And you can see that there is a very different, in this area where we have no cells, there's a very different fluorescence. And in one here, our culture medium is actually fluorescent and creates a background. So this is fluorescence, it's real fluorescence, it's always going to be there. The mounting medium can also be fluorescent, and we have seen this now when imaging your samples on Friday and Monday. We have seen several students who had fluorescent mounting media. In general, it happens in 1 or 2 channels. So these mounting media, they do degrade. Take care of them. Check if they have a sell-by date, if the date is fast. And if it has, then just check this. You take a little slide and you put a little bubble, you make a bubble in the slide, slide with a cover slip with only mounting medium. You have a little bubble there, you image the bubble. If you see the bubble, then it means you have autofluorescence. If the bubble is not visible, so you can use like transmitted light to focus on it and then you image it. If the bubble is not visible in the fluorescence, it means you do not have any autofluorescence in that channel. So that is important. Never image inside the bubble, by the way. So autofluorescence of the tissue can be autofluorescence of the culture medium. It can be autofluorescence of the mounting medium. It can also be, so this is like background from samples. It can also be immunostaining that is not specific. So maybe your primary and your secondary bind, a bit randomly at the bottom. I think we have seen an example. And so these are background. This is really a primary antibody that binds at the bottom of your dish and then a secondary binds to it. This is real fluorescence and it's not going to go. You can take 10 images, it's still going to be there. So this is background, okay? So when you can refer to the sample preparation tip and the lifestyle imaging lectures about this. So the background can also come from imaging conditions. And for example, if I show you here, so here I have a sample that lights up or not, and it looks very, very specific. And actually, is this specific signal, right? It's hard to tell because when you take an image, you don't take a time lapse, like you just take one image. It's like, oh, bizarre. Well, actually, this is only me changing the desktop lamp next to the microscope. So I'm pointing it towards the microscope or away from the microscope. And this is a wide field system. So a wide field system does not throw away the light that comes from elsewhere. Anything that comes in, a wide field system is very light efficient. Any light that comes in is going to go to the sensor. And this is what happens if you shine the lamp or you forget some lamp somewhere. With a wide field system, you'll definitely see it. And if you do not see it that clear, it will anyway decrease the contrast in your images. So just make sure that you do not have any stray light coming into your system. So this is a sensitive camera, and it was with a 10x objective and a wide field system. So turn off the headlamps when imaging with a microscope without pinhole. With a pinhole, it doesn't matter really because the pinhole will throw away this type of light. So another type of background that can come from imaging conditions on single point confocal is the sensor offset. So this is what some of you were talking about. So we have the cameras that have millions of pixels, and we have the detectors on single point confocal. They only have 1 pixel. And there are some things that you can change in the microscope software. There are some things that you can influence, and one of them is the gain of the sensor, of the detector, and the other one is the offset. So the gain will set the level of amplification. So you remember we have a photon, some photons are detected, and then that becomes an electron, and we amplify the electrons, and then we read the electric signal. So this amplification thing is what the gain is. And then the offset is the lowest sensitivity of the detector. So what is the lowest amount of photons that of electron actually that it can that will create a signal. So this is basically the offset is how dim can your signal is, and you see in the image, and then the gain is how bright, how much you're going to amplify the photons that are coming in. So we can have on all microscopes, we have a mask that allows us to see what is saturated and what is underexposed, and very often it's blue and red, so that the red is corresponds to saturation and the blue is underexposure. So if we have a very high gain, we're going to get lots of red because we're amplifying our photons very much, and so we're going to saturate the sensor. And if we have a too low offset, then we're going to get lots of blue like this when we apply this saturation and underexposure mask. And that means that basically we are not detecting any of the weak signals. And so in the background, but also inside the cell. So we will talk about all this tomorrow. But we can influence basically the background with the offset. So we'll talk about this too much. So a low detector offset means a darker background, but if the offset is too low, the background will become solid black. If you remove the mask, you will see solid black. So great, you don't have any, little blue in the background, but there will be no nuances everywhere. And the detector cannot detect the dim signals. And it doesn't matter if it's in the background or inside the cell, it will not detect the dim signals. So you're likely to lose. And also it cannot be fixed after acquisition. So if the offset is too high, the background becomes grayish or blue if you have a blue channel and you put a color. And all dim signals are detected. So you're not losing anything if your offset is too high, but if your offset is too low, you are not detecting the weak signals. That can be fixed later with background subtraction. This one cannot be fixed later. So it's important not to be in the situation where you use the offset to make your background black. So set the offset to the level just above the one that gives you some blue pixels, and then the black background you will get a black background, but no underexposure. So this is important, and always keep the saturation of the exposure mask on. So this mask should always be on. If it bothers you, you change the settings, and then it disappears. Instead of just going like, I don't want to see this blue, I untick the button. So set the detector to get no saturation and no underexposure in the areas of interest. And on HD detectors, this is actually set automatically, but many of us do not have HD detectors. So now I was talking about single point confocal, and now we talk about cameras. So we see that we have all these millions of pixels. And so what happens in there? We have this image with 3 channels. And if we put our mouse a little bit in the outside the sample, we can see that in this channel, we have 105 here. So we have some intensity basically outside the sample. What is that? So this here is the camera offset plus the mounting medium autofluorescence. So basically, cameras cannot deal with values that are negative, but there is always noise. So the value in the background, even if you have no light, the value will increase and decrease a tiny bit. And so the camera manufacturers, they add an offset to their camera to avoid getting in a situation where we ever get close to 0. So it's very, to remove the camera offset and the sample background from images acquired with a camera, what you need to do is subtract the minimum. So you make a region of interest here. So again, region of interest outside the sample, and then you will look at the minimum intensity and you will subtract this from the whole image. So you can use Fiji, the background subtraction tool, to do that. And this is what happens. So here I have a region of interest everywhere, and I'm subtracting it. And after subtraction, I get like a nice black background everywhere, but not everywhere, because in here anyway, my mounting medium is fluorescent, and this has a low contrast, but the images look much nicer anyway. So the fact that you have a little bit of gray in the background does not affect the analysis. So to only remove the camera offset, what you do is that, and I've done this weekend with several of you, you acquire an image with no illumination light. So you turn on your channel, but you remove the illumination and you get an image. And clearly there will be no signal in this image. And so what you will see, the counts that you're getting, the intensities that you're getting in your image is the camera manufacturer offset. So in general, it's 100 or 200, and then there's like a little variation for each pixel. And you can subtract this value from the intensity of each image. So this is the way it works for camera-based system. So let's have a look now. If we have a region of interest in a sample A and it's 2000, the intensity is 2000, and we have another region of interest in another sample, it's 200, and we know that the camera offset is 100 because we have taken this image without illumination. So is really the sample A 10 times brighter than sample B? So let's have a look. If we do not do the background subtraction, we're going to say, oh, yes, my sample A is 10 times brighter because we divide like this and we get 10. But this is the wrong value because the reality is that we have to remove the background first. So we are removing the camera offset. And here we end up with having 1900 and 100. So the correct value is 19. So actually, the sample A is 19 times brighter than sample B and not 10. So it's very important to always remove the background from camera images because there is always an offset. All cameras have an offset, so you must subtract the background from the offset before you extract any intensity information. And this is especially true, of course, if the intensities are dim. Very important. You, of course, treat all the images in the same way, and you report the background subtraction technique in the article when you publish. So you need to keep track of what you've done. Yes, and so what I was saying before is that if you want to actually get this ball to show a little bit more, either you get a bigger ball or you cut the grass. So cutting the grass can be reducing the background, reducing the noise, and getting a bigger ball would be equivalent to increasing the signal. So now we are in the situation where we have, again, this ball here, and here we have this boring background. And it's background because if you take 3 images of this, the grass is always going to be there. But in here, we have maybe, some a bit randomly, some pieces of grass are going to be long and some are going to be shorter, and that comes a little bit randomly. And so this is more like noise. Let's have a look at what noise is now. So now we're talking about signal to noise ratio instead of signal to background ratio. So as I said, the background is something that is really fluorescent, and it's just there and we don't want it, but it's really fluorescent, whereas the noise is random. So this is a very easy technique, and I've done this also this weekend with you guys. Very easy technique to estimate the noise in your images. You take a little time lapse of 3 images without any interval. So if I take this image, so even though it's dim and stuff, you can see that these things are a bit dancing or something. Things are happening. This is a fixed sample. Nothing should move, but things are moving anyway. And this is because of these three images. I can see a difference between the 3 images. So the background and signal, the background here and the signal are constants, but the noise is random. So what changes between the images is noise, okay? So you can see. So the noise comes everywhere. It comes on top of the signal and comes on top of the background. So it's all over the image. But the noise hides dim signal more specifically, and we will have a little look why. It creates an uncertainty, especially when you do image analysis. So it's not really possible to accurately decide. If you want to count the small dots, it's difficult to count them because some of them appear and disappear, like this one, for example. And then if you would want to see the size of the dots, it's also difficult because the edges are not clearly defined. They change from one image to the next. So where is really my signal? Where are my dots? So it creates an uncertainty at the in this image. If now you see I have removed, so I don't know if you can see, but it's still moving a tiny bit. So I am actually playing the movie. So these are also 3 images after I reduced the noise. And what you can see is that it is much clearer where the dots are, how many dots they are, and it's much easier for me to figure out the edges of the dots. Okay, so this image has been the same sample re-imaged after removing the source of noise. We get a more reliable image analysis. So it's very important to deal with the noise and with the background. And these are different things. And if you have a dim sample, it's especially even more important to deal with the noise. So the noise comes from different sources. So what are the different sources? As I said, this is the process. We start with some photons coming in, and with the quantum efficiency, some photons are detected, and then we amplify them, and then we read, and then we convert to a digital signal, then we build the image. We have different sources of noise in this process. One of them is called the shot noise, and it comes from the fact that light itself is random. So it's the photons along the wave, they come with a higher sort of probability, but they come and go. So they might come or not. So it's random. We also have dark noise, which is created by the amplification. And we also have readout noise, which is created by this voltage reading. So the reading of the voltage and the conversion creates also some noise called the readout noise. So there are different sources of noise, and there are different solutions for each of them. And this is all true for cameras and detectors. So the dark noise, the one that is created by the amplification, this is created by the electronics in the sensor, and it's usually very small and negligible, except if you are imaging at single photons, for example. So for most of what we're doing, this is negligible. And there's nothing that we can do on the microscope settings that can help, because this is part of the imaging conditions, but also the specifications, basically, of the microscope of the sensor. So yeah, some cameras have a cooling system to lower the dark noise, basically. And this is true for all detectors and cameras, but there's not much we can do with the dark noise anyway, and it's quite low. So we can just forget the dark noise. We have shot noise. So light is a random process, and there is therefore an inherent noise in it. Sometimes it comes, sometimes it doesn't come. And this is called the shot noise. So this is not created by the sensor. It is created by the fact that we're just dealing with light, and it can never be eliminated. So light comes with some statistical noise. And the thing is that we know exactly how the noise and the signal are related. So the shot noise is the square root of the signal. It's the distribution of the noise, so we know that. So what does that mean? So when we look at shot noise, we can see in these 3 images, even though it's not a time lapse that we're playing, it's clear that this image is a lot more noisy. So we can see this sort of grain, it's like salt on top of our image, compared to this image, which is not noisy at all. So here, what happens is we have a lot less photon in this image, and here we have a lot more photons. Because so in this image, we can say, maybe we have the signal is 4. Of course, it's totally random numbers, but let's say that in this image, the signal is 4, so it's a low signal. The shot noise is the square root of the signal, and therefore the signal to noise ratio is going to be 4 divided by 2, and so it's 2. So 50% of this image is noise, basically. The contribution of the noise in this image is 50%. Now, if we manage to increase a little bit our signal, and now we go from 4 to 16, the shot noise is still the square root of the signal. So square root of 16 is 4, and therefore the signal to noise ratio is 4. Here it was 2. And so the contribution of the noise in this image is 25%. You see that we have already, by going from the signal 16 to 4 to 16, we have increased our signal to noise ratio. And if we now put a lot more signal, and we have tons of photons in here, then we have a shot noise of 55, the square root of 3000, and therefore we have 0.2% noise. This is negligible, okay? So increasing the number of photons that come to the detector will do exactly that. So more photons less contribution of the noise. Even though you can see that the shot noise is increasing from one to an image, the signal increases much faster, and this is because of this square root relationship between the shot noise and the signal. So the consequences in this noisy image is that we can hardly see the big rock, and there's no way we can see any of the little clouds in here and no rocks on the beach. So no details in this image because the noise hides the signal. Okay, and whereas in here we have all the little details preserved. So the shock noise is the square root of the signal, and this is very easy for us to influence. We just need to put more photons. So that's a strong influence in the software settings. And again, it's the same thing for camera-based system and point confocals. How do we decrease the contribution of shot noise? We just need to increase the number of detected photons. So we need to increase the illumination power. If you don't image live samples or if you can afford, we can increase the exposure time. So we will accumulate more photons. So we can also lower the scan speed on a point confocal. So we have longer pixel dwell time. Again, it's the same thing as increasing the exposure time. We're just accumulating more photons to participate to each pixel. And therefore, we have more photon detection, so lower participation of the shot noise. We can open the pinhole, and that will make also more photons coming into the detector, but of course at the expense of the optical sectioning. And then we can do some our work when we design our fluorophores and get better excitation and emission efficiency on our macroscope. And we can also change the fluorophores and use brighter ones. So there's lots of things that we can do, we have spoken about, that will help us decreasing the noise in the images. Make your sample brighter, make the images brighter, basically. So this is true for all systems, basically. And now, so I said that the dark noise, we can't do much about it, and it's anyway very low. Shot noise is very high, and this is the main source of noise. But we also have readout noise, and the readout noise comes from the reading the analog signal, the electric signal, and converting it to a digital signal. So there we also have some influence in the software. And this is very linked to the speed. So in general, this type of noise increases when you want to go faster, and it decreases when you can afford to go slower. And so it's the speed of reading the voltage, the speed of the amplification, and the speed of the conversion. So how can we influence the readout noise? We can lower the amplification or lower the readout rate. So on single point confocals, we should not push the gain of the detector too much. If we push the gain of the detector, we have very few photons to come up that come and are detected, and then we amplify the signal very much so that we can see the image. But what we're doing is that we are actually creating a lot of noise as well, so the image becomes noisy. So a high detector gain on the single point confocal will lead to noisy images. But of course, if you lower the detector gain, the image will become dimmer. So you can compensate by doing what I've said before: increase the illumination power, go a bit slower when you image, open a pinhole, etc., etc. So don't use very high detector gain on a single point confocal. When we talk about cameras, then we have, in general, in the software, it's not always there, but in general, we have something called the readout rate, and in megahertz, and it means that we will go slower. So the maximum speed of the camera will be slower, but we will create less noise. So this is the one that I was showing you about here. We have different readout rates, 200, 540, whatever, it depends. Sometimes they don't give a number, sometimes they give it a name that they say sensitive or fast or something like this. But basically, this is the readout rate. Exactly. Another way to reduce noise, and that is for any noise, so it doesn't matter if it comes from the shot noise or the readout noise or anything, any noise can be reduced by averaging. So in this image, we have not averaged, and the image is very noisy, so you can see how grainy it is. And in this image, we have averaged. And so you see that the noise is gone. But clearly, when you average, what you do is that you make everything a bit smoother. So if you have You know, if I take three images, so the average is basically is that I'm going to take several images and average the values that I get for each pixel. So if I average 2, the noise is reduced by half. But the intensity, so here it's going to be reduced by half, but the intensity in here is going to stay the same. So the real fluorescence, because if you remember, the noise is not real fluorescence. So real fluorescence, like background and signal, will stay exactly the same. If you take several images, they will have the same intensity. So when you do the average, you will get the same intensity. But because the noise comes randomly between the 2 images, you're going to have the noise at different places. And so the noise will be reduced in half, but the signal and the background stay. So unfortunately, it takes double the time to image because you have to take 2 images. And also the edges become a bit fuzzy. So the segmentation of the image is less accurate. And also we bleach more, clearly. So averaging is anyway quite a good way to reduce the noise in the images if you have tried everything else and it doesn't work. So also you have to be careful that when you image for a long time, some fluorophores have a tendency to go into the dark state, and this is what we have seen yesterday, or yeah, maybe. So this you don't want to do, right? So on the single point confocal, sometimes you have the choice in how you average. You should choose the frame averaging to avoid this problem. So how much averaging? Because in general, you have the choice of different numbers, 2, 4, 8, 16, whatever. How much should I use? Basically, what you do is that you estimate the noise first. So you acquire this little time lapse of 3 images, and then you play, and then you ask yourself, does the noise prevent you from reliably answering your scientific questions? So only you can tell. You look at the images and go like, oh, I want to see exactly where this vesicle is, and I cannot see because it's sort of dancing around. If it does, then you can ask yourself, have you tried to reduce the Shoid noise by increasing the illumination, for example? And have you tried to reduce the readout noise? If you have done that as well, then you should, and it bothers you because it's difficult to answer the scientific question, then you should average. You start with 2, you test again, you ask yourself again these questions, and if it's still a problem, then you go to 4. So this is the way to decide how much averaging you should use. You basically test with this little time lapse that I was talking about. So this is true both for detectors and cameras as well, so any system. So the little, I'm just having a quick look here. Right, let's see. Sorry, I'm just going to escape here and have a look. Right, good. Oh, I'm just spot on time. So proud of myself. Here we go. So I'm going to go to my little conclusions here for today. Click and hide. So the phrase signal to noise ratio, SNR, everybody goes SNR, is often used wrongly for both the signal to noise ratio and the signal to background ratio. Both of these have different sources. They should not be confused because they also have different solutions. If you find things in your image that bother you, do not ignore them. Look at them straight in the face and go, how do I get rid of you? Okay, so if it's noise, and you deal with it as noise. And if it's background, you deal with it as background. So the background and the signal are located at stable places. They are real fluorescence, both the background and the signal. And so when you take several images, they will not change places. Whereas the noise is small dots that appear at random locations between images. And so the noise is not real fluorescence. It just shows like fluorescence, but as individual pixels that just keep changing between images. So do this little time lapse to evaluate your noise. The rest is background. Yes. So increasing the signal is an extremely efficient way to improve an image, to improve the contrast in an image, because this is what we're talking about. When we increase the signal to noise ratio and the signal to background ratio, what we do is that we work on the contrast, which we know works hand in hand with resolution. And to increase the signal, we need to choose fluorophores that work for the microscope and increase the illumination and also some more photons, basically, and we can lower the pixel dwell time or make it higher, basically lower the scan speed and the exposure time. So basically more photons, better fluorophores matching with the microscope and more photons to the detector. We are definitely increasing the signal. And decreasing the background and the noise works as efficiently to improve an image. So do not forget to work on the background and the noise if you want to improve the contrast in your images. And the backgrounds and the noise have lots of possible sources and with different solutions. So the background can come from the sample, autofluorescence and all sorts of stuff, or from the imaging conditions. And most background comes from the sample. So it's quite rare that you have stray light like I was showing. And the noise is mostly shot noise and readout noise, but shot noise is the biggest issue most of the time. This is shot noise that you're dealing with. So to reduce shot noise, you need to increase the number of detected photons. And to reduce the readout noise, you can change the detector gain. So reduce the detector gain and compensate by increasing the number of detected photons by the illumination power, for example. Averaging also works, but it has its problems, sending the fluorophores to dark states, making everything a little bit fuzzy, and also bleaching more, taking more time, etc. And also there are some post-acquisition processing that are very efficient at removing noise, especially now with AI. Noise is very easy to recognize in images, so there are lots of AI tools to remove noise. So you need to ask yourself, what is your goal with the image that you're acquiring right now? And ask yourself, is it okay to have noise in this image or not? And background, is it okay or not? And then you deal with the source of the problem. And if you, when you want to publish, you can just go for it and blast the whole thing, put a lot of illumination power, do lots of averaging and everything so that you get a gorgeous image. If your goal is to put it in an article. But of course, clearly, if what you want to put in an article is one image the way you are, that you are acquiring to show how the images that you use for data acquisition, then you show the stuff that you really use, right? If you want to show something else, then you can acquire a beautiful image. But mostly, no. To get data for analysis, you need to acquire an image that shows, that allows you to reliably answer your scientific question. So I want to stop here and I will ask if you guys have some questions. And tomorrow we will continue with all the saturation, underexposure, and things like this. Do you guys have any questions with the signal, the background, and the noise?
Sylvie,
Yes.
I got lost with how you calculate a percentage of noise from these three images you take.
Yeah, so it's just you basically, the signal, right? You take the square root of that. And the square root of your signal is the noise. And then you do the ratio between them.
Okay, but in this, when you take you take this time, no?
Sorry?
When you take the time lapse,
yeah,
then you average.
That's only a visual way. When you take the time lapse, you don't need to see it. So it's very convenient. You don't need to calculate anything.
Okay.
In general, you don't need to calculate. What I wanted to show you with this calculation of the signal to noise ratio, I wanted to show you that if you increase the signal, the contribution of the noise decreases.
Okay.
Yeah. So this is the important thing, is to remember that to fight shot noise, you need basically more photons. That's the way to reduce shot noise, is to have more photons one way or another. But when you want to estimate the noise in your images, just take 3 images very quickly and look at them, and you will see, and you ask yourself, okay, what do I need to analyze? And you see, compared to what you want to analyze, then you will see if the noise is in a way or not. If the noise is not in a way, it's totally okay to have noise in the image.
Okay, thanks.
Yeah. Do we have some more questions? Okay, well, if we don't have any more questions, we're going to go to the workshop Zoom and we're going to have some group discussions about signal to background in your images. So I see everybody else tomorrow, maybe. Ciao.